Good evening, everyone, and welcome to tonight's broadcast on Fiveable. We're going to be looking at helping students master taking derivatives. We're going to be focusing on implicit derivatives and how to take derivative inverse functions. My name is Jamil Siddiqui. I'll be walking you through this evening. We got kind of a small group out there tonight, but if you guys are there, if you just want to give me a little hello in the chat so I know you can hear, we're going to get started this evening by looking at, again, how do we get our students ready to take derivatives and take derivatives well. So I want to remind you to follow us at Think Fiveable, Twitter, Instagram, YouTube. We all have channels where we're putting information out on a daily basis to help you and your students prepare for the AP exams. In this stream, the things that we're going to be looking at and talking about are what exactly is an implicit derivative? Why do we need implicit derivatives? And how do we find the derivatives when we've got inverse functions as well? Okay, I know my students always have a little bit of a hard time at first getting used to the idea of inverse functions. They're very used to using functions like the trigonometric functions, sine, cosine, tangent. But as soon as you start asking them about the inverse functions, the inverse sine or the arc sine, then their heads start to spin a little bit and some confusion sets in. One of the things we're going to do tonight to talk about to help you eliminate that confusion is really working well with your pre-calculus teachers and building a strong foundation with these functions, because once they understand how these functions work, integrating the calculus in with these functions, teaching them the derivatives, not that difficult. It's more just them getting used to using the functions in general. So if you were with me for our first stream about derivative taking, we talked about what I call the one-step derivatives, and these are the derivatives that students just need to know by looking at them. If they know these derivatives, they can just write the answers down. They don't need to show any of their work. And I kind of group them in the following ways. The first one is the derivative x to the n. Again, if the student sees x raised to a power, that's a number. No work is needed. They can just take that derivative directly and write down the answer by using this rule. The next 6 one-steps are the 6 trigonometric functions. And we talked about last time ways that students can learn these trigonometric functions and know them very quickly. If you didn't get a chance to see that, that's in the library, on the Fiveable library in the calculus. You can go back and watch that, and we discuss some different ways that students can learn these derivatives and learn them fairly quickly. It's actually the next set of derivatives that we're going to be talking about this evening, okay? The next 3, the derivative e to the x, the derivative ln of x, the derivative a to the x, all of these cause my students a little bit of trouble in the beginning. And again, the reason is because they're just not as comfortable working with these functions. E to the x, especially the logarithm functions, and then a to the x, kind of foreign to my students at the beginning. And then when we tack on these last 3, the derivatives of arcsine, arctangent, arcsecant, that really throws them for a loop in the beginning, okay? So we're going to talk about each of these derivatives that I mentioned at the end, and ways that your students can really understand them. I had a teacher I was talking to very recently, AP teacher, who said, the number of questions that deal with inverse trig on the AP exam is so low that I feel like it might not even be necessary to teach them and kind of roll the dice and take the chances that there won't be that many points associated with them. You might feel that way because of the number of points that are generally given. But my feeling is that I want my students to be prepared. I want them to understand what's going on. And like I said, with just a little bit of work in pre-calculus, those inverse trig functions actually end up working out pretty nicely. So I'm going to show you how you can get that across to your students this evening. And hopefully that you'll be able to use that and get your students to a place where those last 3 derivatives really aren't that intimidating at all. The last thing I want to put up on the screen before we start doing some problems tonight that we're going to talk about is the derivative in inverse. To me, this is the most convoluted question, or the most convoluted theorem in all of calculus. You ask your students to read it. There's a lot of confusion. You know, the derivative of the inverse function of f of x is equal to 1 over the derivative of f evaluated at f inverse of x. A lot of words going on there, a lot of notation. We're going to take a look at how we can break down this expression and really simplify it so students can understand it. And again, the idea is to make sure our students don't have to memorize these things, because as easy as it is to memorize something, it's equally easy to forget. We want to give them a way that they can follow these things and not have to memorize them and just be able to recreate them as they go. So what I'd like to do now is switch over to my tablet and start looking at some different problems that we can show our students and work through with them. So to begin with, I want to show you a problem that I just did just today in class. My students right now only know the first 7 one-step derivatives. That's it. We've never mentioned anything other than that. But I've tried to really explain the meaning of the notation that's involved. And what's going on with this problem is that dy over dx is important. This is telling us in the top that y is the dependent variable and x is the independent variable. So my students will know that just by looking at the Leibniz notation, dy over dx. And I gave this problem today, and I was kind of curious to see what would happen because I'd never given them a problem that wasn't written in a y equals form or an f of x equals form. So I've repeatedly said to them, the way we take derivatives is we take derivatives of both sides of the equation. I've been drilling that home over and over again. And just a real quick example, simple one, just so you know what I mean. When my students see y equals x squared, they look at that x squared and they're like, well, that's an x to the n, so I can just do that derivative in one step. That's 2x to the first. And instead of just instinctively writing y prime on the left side, the way we do it is we say, what is the derivative of this side? What's the derivative of y? And that's a notational thing. The derivative of y is written as dy over dx. So what they're really thinking about doing is taking the derivative of y to get dy over dx and taking the derivative of the other side, derivative of x squared, to get 2x. So my students are very, very comfortable with the idea of we can do anything we want to an equation as long as we do the same thing to both sides. And in this case, the idea is to take the derivative of both sides. So keeping that in mind, I gave my students the equation 3x squared plus 2y equals 7, and I asked them to take the derivative. And the majority of them, I think every single one of them, the first thing they did was they translated this equation so it would be equal a y equals equation. So they all went, this is the same as 2y is equal to 7 minus 3x squared, and they divided both sides by 2, and they came up with y equals 7 over 2 minus 3 halves x squared. Now, there's absolutely nothing wrong with approaching this problem this way, okay? This is an equivalent equation to the one that I started with. So when my students got this far, they said the derivative of the left-hand side, the derivative of y, is going to be dy over dx. And then they went term by term on the right-hand side, and they said the derivative of 7 halves is 0, and the derivative of negative 3 halves x squared. Well, that negative 3 halves, we call it a free ride in my classroom. We give that constant a ride to the answer, and then we take the derivative of our 2x, and that ends up being negative 3x for our answer. Okay, and that's a totally, completely acceptable answer. But what I was curious to see was, would any of my students just take the derivative of this equation without manipulating it? Because if we just tackle it as 3x squared plus 2y equals 7, and we keep in mind that the word in the directions here is to find. And I want my students to think find means solve. So we need an equation we can solve for a dy over dx. And right now, there's no dy over dx in this problem. So I was very curious to see, would any of my students just go and say, let's take the derivative of both sides exactly the way it looks? Had they done that, the derivative of 3x squared would have been 6x. The derivative of the 2y, well, 2 would get a free ride, and now it's imperative they understand that y is the dependent variable in this problem. So you can't just take this derivative as the way you would an x. You know, if it was 2x, you'd say the derivative is 2 because the derivative of x is 1. In this problem, they have to say the answer is 2 times the derivative of y. And the way we write the derivative of is d over dx, and now it's the derivative of y. That is the key step here, getting students to understand that when you take the derivative of y with respect to x, you can just write the notation dy over dx as the answer. And now on the other side, the derivative of 7, pretty straightforward. The derivative of 7 is 0. So from here, we're asked to actually find dy over dx. And for the first time, we can actually think about this in terms of solving an equation and isolating for a variable. If we think of dy over dx as the variable we're isolating, that means we need to get this guy by itself. So let's subtract 6x from both sides, and then let's go and divide both sides by 2. And in doing that, we get dy over dx equals negative 3x. Now, what I hope you notice is two things. The first thing, it's the exact same answer we got when we isolated for y. The second thing, there's nothing in the law, in the rules about taking derivatives that says it has to look like y equals. And that's really the key here to understand. We don't need a y equals equation to be able to take a derivative. And if you get your students comfortable with that from the beginning, when you're first taking derivatives, when we move to implicit derivatives, things are going to go a lot smoother. So let's move on to the next slide. If you guys have questions at any point in time, feel free to put it out in the chat. I'm happy to answer any questions you have. When we're looking at this example, it looks very similar to the one we just saw. But if I gave this to my students and they tried to solve it for y, there would be all sorts of problems. This is not easily solved for y at all. So the idea of trying to get y by itself is just not going to fly in this problem. So that's where the idea of taking a derivative of both sides really comes into play. So in this case, what we want to do is we want to look at this and we want to say, can we go term by term and take the derivative of this equation? So I'm going to start with the 3x squared y, and I'm going to say, how would we take the derivative of this? It's not exactly one of those one steps. We've got a mixture of variables. We've got x's and y's in the same problem. So it's not going to look exactly like what I call those one steps. So instead, what we've got to do now is say, what are our other derivative rules that we've got? And this is clearly going to be a product rule. We've got factors here. We've got 3x squared. We've got y. So what I'd like to do is set up a product rule. The way I always set up a product rule is I kind of take the two factors and I separate them in this little grid. It's kind of an organizer that I like to use. So I'm taking the derivative of 3x squared as one factor and the derivative of y as the other factor. So if I just do it in this grid, now all I've got to do is focus on one factor at a time. So on the left-hand side, I'm just asking, what's the derivative of 3x squared? That is a one step, so I can say that's 6x. And on the right-hand side, I'm looking at that one and I'm saying, what's the derivative of y? But when you're doing this one, you're looking for the derivative of y, that again ends up being a notational kind of thing. So the derivative of y is literally just written d over dx for the derivative of, and now y. So now the way I remember the product rule is I use this graphic organizer, and I know it's this diagonal plus this diagonal to assemble the product rule. Those of you who may use the derivative of the first times the second plus the derivative of the second times the first, you can see that's exactly what I'm doing. The derivative of the first is this 6x. So again, I'm going to go along this diagonal right here, and I'm getting 6x times y. That's the derivative of the first times the second. And now I'm going to do my plus up here. And now I'm going to come back and go the other direction. And that's the derivative of the second times the first, which is going to be 3x squared and then dy over dx. So all I'm doing is going term by term right down the line and making sure that my students are comfortable with taking the derivative of this as a product. So now I go to the next one. And when I go to the next term, this is just 2x. And derivative of 2x is straightforward. That's one step. Just do that by looking at it. So that's going to be plus 2. And now it's time to go to the other side of the equation and make sure we take the derivative correctly over there. But this time we're taking the derivative for y. Now, the mistake my students make all the time is they think that y is the independent variable, and they try to answer this as a one-step saying it's 8y. The key here is to make sure they understand that since this is being done with respect to x, I call it a variable mismatch. I'm trying to take the derivative with respect to x, but I only have y's. But we know because of this relationship that y is not a constant. Every time x changes, y does have to adjust. So it's a variable as well, but it's got to be the dependent variable. So instead of trying to take this as just a one step, what we've got to do is we've got to say, can we use a different rule? And the idea of getting your students used to the chain rule is imperative here, because what's going to happen here is this is a chain rule. So 4 is a constant factor. It goes right to the answer. And now we're looking at taking the derivative of y squared. Well, I like to think of this as a chain rule where the outside function can be written right over here. The outside function can be written as something squared, and that inside function can be written as y. So when I do the chain rule, we say take the derivative of the outside. In this case, that's 2 something to the first. Copy the inside, which is our y. And then I like to say take the derivative of our inside, but derivative of is written d over dx, and our inside is y in this case. So that is how we would take the derivative of the inside. So again, chain rule in effect. The derivative of the outside is 2 something to the first. Copy that inside, get y. And the derivative of y in all these problems is going to be labeled as dy over dx. Just to give you the complete picture, some people like to use the y prime notation instead of dy over dx. That is also completely acceptable. You don't have to use dy over dx. I personally like that a little better. I think the Leibniz notation shows who the dependent and the independent variable is, but the Newton notation of y prime is also acceptable. So all I've done is I've just gone term by term, and I've taken the derivative of this equation. So now comes the key word in this problem. That's kind of a hidden one for some students. And that key word is up here, and it's back here to it being find. Find means solve. We need to solve this equation for dy over dx. Well, the original equation up here didn't have any dy over dx's in it, but by taking the derivative of both sides, we now have several dy over dx's in it. So I'm just going to clean this up real quickly. It's 6xy plus 3x dy over dx plus 2 is equal to, and this is going to be 8y dy over dx. So at first, my students are kind of thrown for a loop because they're used to solving for x, and it takes a minute to say, well, we can solve for whatever notation we want. In this case, we're trying to isolate dy over dx. And now this leads to us kind of asking some questions like, what are the general rules to solving equations? And my students will tell me, well, you got to do the same thing to both sides, which is great. But then the other thing you have to remember, going back to their early math careers, is if you're solving for a variable, you want to get all those variables on the same side. Well, we're solving for dy over dx in this problem. So we've got to get all the dy over dx's on the same side. In order to do that, I'm going to make this left-hand side the side that doesn't have any dy over dx's. And I'm going to make this right-hand side the side with the dy over dx's. So basically right now I'm just copying things down. But now what I've got to do is I've got to take this expression right here, and I've got to subtract it to the other side. And what we've done now is we've accomplished getting all the dy over dx's on one side. Well, once you've got that, you're closer to solving it, because now the question is, how do you get the dy over dx's away from everything else? And these are the questions I like to ask my students. I don't want to show them how to do this problem. I want them to think about the algebra they've learned in the past so that they can come up with the method of solving it. So this one takes a little bit, but eventually someone says, well, if I want to get the dy over dx away from everything else, how about I just factor it out? How about I treat it like a common factor, and I pull it out, and I leave that 8y minus 3x squared on the inside. On the other side, we haven't touched it. It's still 6xy plus 2. And now what we've got is that dy over dx factored out. And as soon as that dy over dx is factored out, we now can isolate that dy over dx by dividing both sides by this factor here, 8y minus 3x squared. And that will get the dy over dx by itself, which I'll write over here. And we'll end up with the answer dy over dx is equal to 6xy plus 2 over 8y minus 3x squared. And that is going to be left as our final answer in this case. So something to keep in mind when you go through this with your students for the first time, they're very used to just having x's. I mean, the majority of derivative problems you do at the beginning of a calculus course, they're all functions. So when you take the derivative function, you end up with a function. You've got to kind of remind them that this problem, we couldn't get this as a function. We couldn't isolate the y in the beginning, but that's not a problem. I mean, just because it fails a vertical line test doesn't mean it can't have slopes of lines tangent. There's still going to be slopes associated with this. So just kind of breaking them in with the idea that non-functions still have derivatives, and they depend not just on the x value, but they depend on the x and the y value to determine the slope. So that's kind of the idea that you want to bring out when you're talking about implicit derivatives. So the next thing I really want to talk about this evening is I want to talk about inverses and some work we can do in pre-calculus to get inverses your students kind of ready for it. Before I do that, I take it back. I do have one more example I want to look at. So a to the x is one of the what I called one-step derivatives from earlier. And I know a lot of students who just go and they say, okay, well, this is the rule. Here we go. The derivative of a to the x is ln of a times a to the x. As long as I memorize that, I'm going to get it right, and I'm just going to do it from memory. And although it might work and it might get some answers, I feel much more comfortable if my students can figure out how to derive this problem without having to memorize it. So we like to talk about this problem the following way. We look at it and we say, okay, can we just take the derivative directly? And because we're trying to prove that, we're not allowed to use this idea to do it from the beginning. So we can't take it directly. So then I start asking my students, well, are there any derivative rules we can use on this? And the fact that it's got an x in the exponent really is what my students get hung up on. So that discussion inevitably turns to me asking them, what part of this problem don't you like? And they respond, the exponent has a variable in it. Well, that leads me to ask them, do you know any ways to get variables out of the exponent? In my pre-calculus class in my school, we work very hard to get students to understand that the way you can bring exponents down is you can use logarithms. So I usually get one or two kids who remember from pre-calculus, well, can I use a logarithm to do that? And we stress the natural log the most in pre-calculus. So by taking the natural log of both sides, and I want to rewrite how I do this. When we take the natural log of both sides, the way I want my students to write that is the following way. I want them to write the natural log of the left side is going to equal the natural log of the right side. And now, once it's set up, now I can fill in the left side as y and the right side is a to the x. Now, students at first are not going to love this because natural log in their minds usually complicates things. But we've got to explain to them that natural log is actually something that makes calculus, makes math for that matter, just a simpler thing. Because we've got rules for logarithms. And because this is a logarithm, we are now allowed to bring down that exponent. So this becomes x times the natural log of a. And now you have to ask your students, what would you rather take the derivative of? This top line, where we're not sure how to do it unless we memorize it, or this bottom line, where we've got some rules we can make use of. So I'll trade in the fact that I'm no longer written as y equals for an equation I can now take the derivative of. So when we go to take the derivative of this, let's start on the left-hand side, ln of y. Not a one-step because y is not the independent variable. So we've got to treat this as a chain rule. And the derivative ln of something is 1 over something. So that's the derivative of the outside. Copy that inside, make it a y. And now the derivative of that y, again, stressing that we're going to write this as notation, the derivative of d over dx, and now the derivative of y, that gives us the answer to the left-hand side. We go to the right-hand side, and my students always want to use a product rule, but if we look at this a little more closely, we're going to realize that the ln of a is a constant. So we can give ln of a free ride to the answer, and then the derivative of x is just simply 1. So now we've taken the derivative of both sides. Let's remember our directions. Our directions said to find dy over dx. I now have an equation with dy over dx. Let's isolate it. Let's multiply both sides by y. I'll write this up here. So I'll get dy over dx is equal to the ln of a, and I'm going to put that in parentheses to show that's a factor staying together, times y. Technically, I've answered the question here. I've answered what dy over dx equals to. But the rule that we use in my class is if we start with a function of x, we want to end with a function of x. And a derivative is a function, and when I look at this derivative, it's depending on y, and I want it to depend on x. So I always kind of say to my class, wouldn't it be nice if we knew something about y, if there's some information we had that could help us work with y? And inevitably, they go back and they remember to look at the beginning, and we are told that y equals a to the x. So we can make that substitution at the end, and then we'll have dy over dx equals the ln of a, and instead of y, we're going to replace that with a to the x, and all of a sudden, students do not need to memorize this at all because they can derive it with a couple of quick steps and using logarithms. So this is the type of idea that I want to come out with to show you tonight, how to get your students to understand these derivatives and avoid memorizing them at all costs. But before I do some more derivative work, we got to take a step back and we got to look at some pre-calculus. So the next example, you're going to wonder what we're doing with this one tonight, talk about AP Calculus, but to me this sets the tone for a lot of the inverse work we're going to talk about. I asked my students, how do you solve this equation? And I am sure that you do the same thing, and you're going to see a lot of this. You're going to see, well, let's multiply both sides by 5. and then you'll cancel that, and you'll get 3x plus 2 equals 20. And then you'll see a law of, well, let's subtract 2 from both sides. And you'll write it like this, and you get 3x equals 18. And then you'll get, well, let's divide 3 on both sides, and you'll get x equals 6. And although there's nothing wrong with that process there, I try to get my students to use a little bit better notation. And it seems very long and drawn out. I'll be the first to admit my students think I'm wasting their time when I show them this, but I know the payoff is going to be when we get to some of these more complicated functions. So when we start this problem, this is what I like to ask them. What's the first step? And they're going to tell me, it's going to mirror what we just said, we're going to multiply by 5. But then I follow up with, how do you know you want to multiply by 5? And what I'm trying to draw out of them is, where do inverses come into this expression? And how do we really just talk about using inverses in this expression? And that's going to be the key when we get to the more complicated functions. If I can get them to talk about inverses correctly with the simple functions that they understand, they're going to see the structure and how it's going to work with the more complicated ones. So I'm looking for them to tell me we are going to do multiplication by 5 because it's the inverse of division by 5. And they're all going to say multiplication is the inverse of division. I really, truly believe it's important to put the 5 in there, that we're going to multiply both sides by 5 because it's the inverse of division by 5. And then I even go as far as to make them write it this way, which drives them crazy. But I make them say, okay, let's multiply both sides by 5. And the way we do that is we use this idea of a template where we're multiplying both sides by 5. And it looks like that. And now we fill in the left side. We fill in the right side. And if we've done this correctly, inverses are going to do their job. They're going to cancel out when applied directly. And the inverses we have here are multiplication by 5 and division by 5. So those will cancel out. They're being applied directly. And now we've got 3x plus 2. And on the other side, we simplify it to 20. So now, again, we ask, what's the next step? And they're going to say subtract 2 on both sides. But remember how we wrote it over here, okay, kind of that vertical alignment. I want them thinking about this as functions. So functions need a place for an input. If we're going to subtract 2 on both sides, I want to show the left side minus 2 equals the right side minus 2. And you can imagine that my students are going to feel like we're wasting time on this easy example, but it's going to pay off big when we get to the more complicated functions. So now when they do this, they're now going to go ahead and fill in this side with 3x plus 2 here. They're going to fill in this side with 20. Inverses, if they're applied correctly and directly, are going to cancel each other out. That's what that plus and minus 2 are going to do. We're going to be left with 3x on this side, and we're going to be left with 18 on the other side. So now the next question is, what's the next step? They're going to tell me to divide both sides by 3. But really what I'm asking them to do is, how do you show me divide both sides by 3? And we're going to get them hopefully to say, well, the left side divided by 3 and the right side divided by 3. And now that I've got that set up, I can put the left side in. I can put the right side in. Inverses applied directly will cancel out. We're going to get x, and it's going to be equal to the simplified version here of 6. We go through this problem. My students are kind of wondering why we're doing this basic algebra kind of math in calculus. But because I know we're going to want to talk about these types of examples in calculus. And now they are not as familiar with the inverses, and this is going to slow them down. So we have to get our students prepared to do this. So if I can go through these two examples with you to show where it's going to pay off, I think it's going to be very advantageous for us as we start looking at the derivatives of these. So in this first example, we ask, what do we want to get rid of? And the answer is going to be the multiplication by 5. So the inverse of that, my students have to tell me, is division by 5. So I want my students to say, the left side divided by 5 is equal to the right side divided by 5. And then they're going to fill in 5 ln of x minus 4, and they're going to fill in 7. And when they do that, these are going to cancel because those are multiplication by 5 being applied directly to division by 5. So those cancel, and we're left with the ln of x minus 4. And now on the other side, we have 7 over 5. Well, it's this next step that I've been building up to. This is the one that's going to pay off. I now want to get rid of the natural log. And my students are going to be able to tell me that that's a logarithm, and the inverse of a logarithm is an exponential. So if I just say what's the inverse of a log, they're going to say an exponential, and that's not quite enough information. So just like before when I said what's the inverse of multiplication, the first part, I didn't stop there. I said what's the inverse of multiplication by 5? And their response was division by 5. Well, now I'm going to ask what's the inverse of the logarithm of base e, because that's what natural log is. It's log base e. So when I say what's the inverse of log base e, instead of just saying an exponential, they're going to say exponential base e. And now when I ask them how to write exponential base e on both sides, they're going to have to come up with writing it like this: e to the something on both sides. So when we fill in the ln of x minus 4 on this side and 7 over 5 on the other side, they're going to know that this is a log base e and an exponential base e acting on each other directly. We're going to be left with x minus 4, and now we're going to have e to the 7/5. For the last step, we got to get rid of that subtraction by 4. So they're going to tell me we got to do addition by 4 on both sides. We're going to set it up like that. We're going to put in the left side of x minus 4, the right side of e to the 7/5. Inverses directly on each other are going to cancel. And we're going to be left with x is equal to e to the 7/5 plus 4. Everything I'm doing here for the last two problems is designed around the idea of getting my students comfortable with the idea of saying, let's do exponential base e to both sides. When we're going to look at one more example of this, on the other side, you're going to see it happen again. What do I want to get rid of first? The addition by 2. So we're going to do subtraction by 2 on both sides. Then from there, what's going to happen is we are going to do 3e to the 5x plus 2 on this side. We're going to do 7 on the other side. The inverses will cancel directly. So we've got 3e to the 5x equals 5. The next question is, what do we want to get rid of next? In this case, we'll get rid of multiplication by 3. So we're going to do division by 3 on both sides. We fill in the sides, 3e to the 5x and 5. The 3's cancel directly. E to the 5x equals 5/3. And this is the step that it pays off on. Because now when my students say, I want to get rid of exponential base e, they're going to know to say log base e to both sides. And the way you write log base e is you write the natural log of both sides. So it's going to be e to the 5x. The other side is going to be 5/3. And now the inverses are being applied directly. So we're left with 5x equals the ln of 5/3. And then just quickly as a last step here, we're going to multiply both sides by 1/5 or divide both sides by 5 to get rid of the multiplication by 5. And I'll just write that out as 1/5 ln of 5/3. Because I think you've got the idea now of how we're going to do the same thing to both sides to get inverses to cancel out. So where does this go next? Well, again, a little bit of pre-calculus before we can get into the calculus. We want to talk about the inverse trig functions now and how we can get our students to understand them and get those problems correct with as little work as possible, or just understand a little memorization as possible. That's what I'm trying to say. So we've got the arc sine of 1/2 here. A couple of different ways you can think about this, but what I like to do in this problem is I like to have my students think of this as I'm looking for an unknown. Let's just call it y or x or whatever you want. Okay. And as a matter of fact, I'll probably just even call it x in this first one. So this is solved for x, but not in a way that my students can simplify very easily. So again, I ask them, what is it about this problem you don't like? And they're going to tell me, with no uncertain terms, that they're not fans of this arcsine guy. So I like to say to them, well, you're in charge of the equation. If you don't like arcsine, you don't have to have it. So what's the inverse of arcsine? And they're going to tell me that I want to do the sine of both sides. And they'll understand that this is what the next step should look like. We're now going to fill in arcsine of 1/2 on the left. We're going to fill in x on the right. And all of a sudden, these inverses are canceling. And now we know that our original equation is the same equation as 1/2 equals sine x. My students have a chance of understanding this because we like to go back to the Cartesian coordinate system and think about our triangles in this situation. So I'm looking for a guy who's got a sine of 1/2. What that's going to do is it's going to give me something in that first quadrant, and I'm going to have an opposite side of 1. I'm going to have a hypotenuse of 2, and my students are going to recognize this as a root 3, 1, 2, root 3 triangle. And that means I've got a 30-degree angle down there, which means that as a radian, this is going to be pi over 6. Now, at this point in time, you can have the conversation about, do you want to treat arcsine as a function that has only one output, or do you want to treat it as a relationship that can have multiple outputs? That's completely up to you how you want to handle it. Tonight, I'm just going to stick with it as a function. So we're looking for just the one output we would get, and that's going to be pi over 6. So this is one way of getting your students to kind of understand arcsine by relating it back to something they already know, and that's sine. Okay, my students are very comfortable with sine at this point. Getting them used to arcsine is the real trick. So if we take this one step further, another important thing that needs to be done in pre-calculus is to get students to understand that arcsine is nothing more than an angle. All inverse trig functions are angles. That's something I have my students actually repeat and kind of chant in class the first day we talk about it. Inverse trig functions are angles. And that really pays off because some of these expressions start to make a lot more sense than they would otherwise. If you look up here, we're saying that the arcsine of 1/2 is being renamed as x, okay? Well, if you come down to this equation, where's the x? The x is the angle of the sine. So arcsine is an angle. Another thing that drives that home is when we finally answer this question, we say that this answer, the arcsine of 1/2, is actually equal to pi over 6. So again, they're all used to pi over 6 as an angle. Now we're just making them understand that inverse trig is another name for these angles. And the more you can drive that home in pre-calculus, the happier you're going to be in calculus. So we'll look at one more pre-calculus example, then we're going to jump back to some calculus stuff. The next pre-calculus example I want to look at is this guy. And the first thing I want to do is convince my students this makes more sense than it looks like, because arctangent is an angle. Inverse trig functions are angles. So this is just asking me to take the secant of some angle. Well, one thing I didn't say to you before, I should have mentioned, is in my class, whenever we're talking about inverse trig, we say all inverse trig functions are angles. And then we like to follow that up with all angles come from triangles. And then finally, all triangles can be drawn. This is something all of my students have written across the top of their page in notes in big letters. Inverse trig functions are angles. Angles come from triangles. Triangles can be drawn. Why do I want them thinking that? Well, it's for the following reason. We're going to focus just on the arctangent part of this just for a moment. Okay? So if we think about arctangent as being an angle, okay, it's going to come from a triangle. So what I'm going to say now is let's call this angle right here the arctangent. All right, so let me label that as arctangent. And when I say arctangent, in this case, it's the arctangent of 1 over root 3. Well, again, what do students have to remember? If we go back to what I just showed you, if we call this x, we can now take the tangent of both sides and turn this into the tangent of something equals the tangent of the other side. Put in arctangent of 1 over root 3 here, put in x, and cancel those inverses directly. And we've got that we're looking for a triangle that satisfies this type of expression. Okay, so what do we know about tangent? Tangent is the same as the opposite side over the adjacent. So when we go to this triangle, the opposite side's got to be labeled as a 1, and the adjacent's got to be labeled as a root 3. We know from the Pythagorean theorem or from our geometry, this is a 1, 2, root 3 triangle. So all of a sudden, we now have a picture of what the arctangent looks like. And we'll just move that over there. So we know arctan is an angle. That angle comes from this triangle over here, and that triangle has now been drawn. But we're not done, because if you go back to the original example, it asks us to take the secant of this angle. Well, this is where I make use of some creative mathematics here. This guy over here, this arctangent, that is a picture of the angle I want to take the secant of. So I tell my students, let's take the secant of this angle, and I write it just like this. They laugh the first time I do it, but then they realize this is not such a bad idea. We're taking the secant of that angle. Well, secant is defined as the adjacent side, the hypotenuse over the adjacent. So when they look at this, they're like the hypotenuse is 2 and the adjacent is root 3. So all of a sudden, taking the secant of an arctangent actually makes sense, and it's something they can draw. And because they can draw it, they can really start to really understand it well. So this is kind of all stuff that I work together with my pre-calculus teacher to make sure my students have this stuff down really, really well after their pre-calculus course. Because if they understand the inverses, if they understand how the inverse trigs are angles, when we get to calculus, things are going to go very, very smoothly. So let's take a look at this example. This is considered to be one of the one-step derivatives. Students can just write this down if they remember it. But if you take a look at those inverse trig derivatives, they're very, very similar. A lot of x squareds, a lot of ones, some square roots. It's very easy to get them mixed up, confuse them. So I always want my students to be able to derive this if they have to. So let's take a look. If I want them to take the derivative of y equals arcsine of x, the first thing they're going to tell me is they don't like the arcsine. They're not comfortable with it. But the good news is it's their equation. They can do whatever they want to as long as they keep the balance. So how do you get rid of arcsine? You use the inverse. And the inverse of arcsine is the sine. So they might start by writing this on both sides. Putting the y there, putting the arcsine here. The inverses are acting directly on each other. So all of a sudden, this equation now becomes the sine of y equals x. They now have a choice, and it's totally up to them. Do they want to take the derivative of this equation back here in the beginning, or do they want to take the derivative of this new equation, which is an equivalent equation, so its derivative will be the same? Well, the first time through, my students don't want anything to do with arcsine, so they're more than willing to take the derivative of the sine y equals x equation. And this is where the ideas of implicit derivatives are going to come through loud and clear, because we've got to take derivative sine, but this time it's sine y, and y is not the independent variable. We've got to take with respect to x. That means a chain rule on this example. So the outside function here is the sine of something. So the derivative of sine something is cosine something. Copy that inside, which is y, and the derivative of that y is written using our notation, dy over dx. On the other side, we've got the derivative of x with respect to x, which is actually really nice. So that's just a 1. So at this point, we go back to what the directions say, which is find. I've got an equation with dy over dx in it. I want to isolate that dy over dx. So I'm going to get dy over dx equals 1 over cosine y. Now, this is a correct derivative for arcsine x, but remember my rule, if you start with a function of x, you got to end with a function of x. Having a y in here is going to kind of wreak some havoc with us trying to get some answers on the AP exam. So again, the question is, can we do anything with that y? And the answer is most definitely yes. Because if we go back to the beginning of the problem like before, we are told that y equals arcsine x. So let's replace that. So now we've got the cosine of the arcsine of x in the denominator. Not bad. It's now a function of x, but your students, if they're anything like mine, are not going to be super comfortable with this expression. And that takes us back to the type of example I just showed you. Can we take the cosine of an arcsine? Well, if arcsine is an angle, which it is, and all angles come from triangles, I can go now and label this as the arcsine of x. And then I just have to remember that the arcsine of x is the guy whose angle is, whose opposite side is x, and whose hypotenuse is 1. So we now have 2 of our 3 sides labeled. Using the Pythagorean theorem, we're going to find out that the remaining side is the square root of 1 minus x squared. And now I know what my angle arcsine looks like. In this example, I'm being asked to take the cosine of that angle. So you're going to see me write the cosine of this. And all of a sudden, the cosine of this guy is equal to the adjacent side over the hypotenuse. And that ends up being the root of 1 minus x squared, which means when I come down here, my numerator stays 1, but I can now simplify the cosine of arcsine of x and make that the square root of 1 minus x squared. And that is the one-step derivative for arcsine. So At any point in time, if my students do not remember this as a one step, not a big deal. They go through this process, they prove it, and they find out that the derivative of arcsine x is 1 over the square root of 1 minus x squared. So I really like this because I am so worried about my students confusing their inverse trig derivatives. This gives them a safety net. They can always make sure that they've got it right. So what I'd like to do is go to the next one, which is arcsecant of x. And I'm just going to give you guys maybe 30 seconds or so just to get this started. I'm going to take a drink of water, and then we're going to come back and take a look and see how you guys are doing. The idea here is the same as the arcsine. Arcsecant is one of the more common derivatives. A lot of students will memorize it, but this is the one that gets confused. Okay, there's a couple extra pieces in the arcsine derivative, so I always like to give my students the safety net of being able to derive it. We'll go through this one a little more quickly. We're going to start by saying if we start with y equals the arcsecant of x, let's take the secant of both sides. When we do that, we're going to get the secant of y is equal to the secant of the arcsecant of x. Well, secant and arcsecant are going to cancel out, and now we're just left with the secant of y is equal to x. Again, now that idea of an implicit derivative comes into play because we're taking the derivative of y with respect to x, which means my secant y is going to be a chain rule. The derivative of the outside is going to be the secant something times the tangent of something. We're going to fill in that inside of y, and then we're going to take the derivative of that, which is d over dx of y, or the dy over dx notation. On the other side, again, kind of nice, we get the derivative of x, and that's just going to be 1. And now we're going to isolate the dy over dx, and we're going to get 1 over the secant of y tangent of y. But we're in that dilemma again where we started with a function of x, we want to end with a function of x. So we've got to replace those y's. So that's the secant of whatever y is going to be, the tangent of whatever we're going to replace y with. But if we go back to the beginning, we know that y is equal to arcsecant x. So we fill in that angle. And something nice happens right away. The first thing that happens is secant and arcsecant are inverses acting directly on each other. So that just becomes x. And now the question is, can we do anything with the tangent of the arcsecant? But this is where every trig function is an angle. Every angle comes from a triangle, and every triangle can be drawn comes into play. So I make my triangle, and this time I want an angle of arcsecant of x. So I label that as arcsecant x. And now I remember that the arcsecant of x is the angle whose secant is x. So that means that the hypotenuse is going to be x, and the adjacent side is going to be 1. From here, we've got to find the opposite side using the Pythagorean theorem, but that's going to be the hypotenuse squared minus the leg squared under the square root, so we get the square root of x squared minus 1. So now that we know what our angle looks like, arcsecant is very tangible now, our students can understand this. Our job is to take the tangent of this guy, the tangent of the arcsecant. And that will equal the opposite side over the adjacent side. But since the adjacent side is 1, this is simply the square root of x squared minus 1. Keep in mind, the reason we're doing this is because we are looking for the tangent of the arcsecant to fill in here. And we have just found the tangent of the arcsecant to be the square root of x squared minus 1. And all of a sudden, we now have the derivative for arcsecant. Okay, no need to memorize it at all. You can just do it by creating it. And I'll be honest with you, the majority of my students will eventually end up learning these and knowing these through memory. But the first 5 or 6 times they do it, they go through this process, and this helps them to remember it. And it really pays off, and it actually saved me 1 year because I only teach arcsine, arctangent, and arcsecant as one-step derivatives. And the reason for that has to do with the integrals and going backwards. So I only teach 3 of them. 1 year, the College Board came out and they asked a question that dealt with arc cosine. And my students did not know the derivative of arc cosine as a one-step. So on the fly, they actually had to prove it. And this was an example similar to the one that was on the College Board test that day. And they had to start by saying, okay, I don't know how to handle arc cosine. So arc cosine is the thing I don't like. So can I get rid of it? Well, the inverse of arc cosine is the cosine. So they took the cosine of both sides. And you're going to see a very similar thing happen here because arc cosine and cosine are inverses acting on each other. So we end up with the cosine of y equals x squared. And they were very, very willing to take the derivative of that equation. Much more comfortable with cosine y and x squared. So the derivative of cosine y, that's a chain rule. The derivative of cosine of something is negative sine of something. Copying the inside y and then taking the derivative of that y is dy over dx. So there's the chain rule being done on the left-hand side. And on the right-hand side, the derivative of x squared, that is with respect to x, so that's straightforward, 2x. So when we get this far, we know that dy over dx is equal to 2x divided by negative sine y. We'll put the negative up in the top. And now we're right back where we were in these other examples. I've got a function of x I started with. I want a function of x I want to end with. Let's replace that best we can. So this becomes the sine of the arc cosine of x squared. And now we've got to draw that triangle and figure out how to handle that. So what does the arc cosine of x squared look like? Well, the angle is arc cosine of x squared, which means this is the angle whose cosine is x squared. So the adjacent side is x squared and the hypotenuse is 1. And now we just got to make sure we don't make a mistake on our Pythagorean theorem. So we're going to get the leg squared plus the leg squared is equal to the hypotenuse squared. We know that our first leg is x squared. We know that our hypotenuse is 1. We know we're looking for the other leg. So x to the fourth plus leg squared equals 1. So doing a little bit of arranging here, we're going to get that the leg is equal to 1 minus x to the fourth, and we're going to take the square root of that. So our missing side is the square root of 1 minus x to the fourth in this problem. Now remember, we are looking for the sine of this angle. So we're going to come back up here. We're going to take the sine of this triangle. And when we do, the sine of this triangle ends up being, I'm just going to squeeze it in right here, the sine of the arc cosine of x squared ends up equaling the opposite side, which is root 1 minus x to the fourth, over the hypotenuse, which is 1. So we come back down here and we say our numerator stays 2x with a negative. The entire denominator is that sine of arc cosine of x squared. We just found that to be the square root of 1 minus x to the fourth. So the fact that my students were only familiar with the 3 one-steps, arcsine, arctangent, and arcsecant, really didn't hinder too many of them, because if they remained calm, they just said, I don't like arc cosine. That's what I want to get rid of. I'm going to do the cosine on both sides. If you have any questions or comments, you want to pop them over there in the chat, please do so. I'm happy to answer anything as we go along. I do want to look at one more example that is very popular on the AP exam. This is an AP style question, and this deals directly with that last formula I showed you for the derivative of the inverse. Again, I have a hard time with that. I have a hard time reading it. I have a hard time using the notation. I would like to show you how I prepare my students to handle that derivative without having to memorize that formula. So as my students look at this problem, they're going to notice a couple of things. And the first thing they're going to notice is what I hope is this right here, that g of x is the inverse function of f of x, okay? As soon as they recognize that, I tell my students, write down the definition of the inverse. And the mathematical definition of the inverse is that if I take f and I apply it to its inverse function g, inverses will cancel off applied directly. This will end up equaling x, because that f will cancel with that g, and I'll just be left with x. So there's our mathematical definition of inverse. And I always encourage my students, as soon as they see any mention of inverse functions, like g of x equals the inverse of f, write that down right away. Because now what we're looking for is g prime of 21. Now, to find g prime of 21, most of my students are going to want to find g prime of x first. And to find g prime of x, they're going to want to find g of x first. So what they're going to try to do in this problem is find the inverse of this f of x. And they might switch the x's and the y's and start trying to solve that for y. And sometimes that may be a very simple, straightforward process. Other times it might not be. This is one where if you try to find this actual inverse function, you're going to run into some problems. So instead of trying to literally find the inverse, what I'm going to do is I'm going to use notation as my guide. I have this expression right here, and the beauty of this is it's true for every set of inverse functions, okay? If it's true for every set of inverse functions, it's true for the inverse functions in my example. I want g prime. There is a g of x right here. If I go to take the derivative of this guy, I am going to get a g prime popping out somewhere. So what I tell my students to do is just take the derivative of the notational definition of the inverse. So as we look at this guy, the left-hand side is f of g of x. That's a chain rule all the way. That's f prime of something. We're going to copy the inside now. That's g of x. So there's the derivative of the outside. Copy the inside. And now the derivative of the inside is g prime of x. On the other side of the equation, we're going to take the derivative of x, and the derivative of x is 1. What I hope you're noticing is the students wanted to find g prime of x in order to find g prime of 21, and there is what we're looking for. There is g prime of x. So now we're going to isolate the g prime of x, and I'm going to divide both sides by the other factor of f prime g of x, and I am going to be here. Now, your students are not going to be super comfortable with this because they feel like there's no explicit function, that we're not really doing any math. But the more you get them used to notation, the more you get them practicing how to manipulate notation, the stronger they're going to be at this. Because now all I'm looking for is g prime of x, so I can plug in 21. I can literally do that with the notation. I can say, based on what we just found, that g prime of something is equal to 1 over f prime of g of something, because that's where my inputs are going to go. So I want to put 21 here. I want to put 21 there. So now, how convenient. I'm looking for g of 21, and that's part of the given information. So the next step here is to say this is really equal to 1 over f prime of 3. And all of a sudden, I no longer need an explicit expression for g of x at all. G of x has been taken out of the problem, and now I've related it back to the original function f of x, which is going to work great because f of x is given up here, which means we can find f prime of x because the derivative of 3x squared minus 2x. That's going to be 6x minus 2. And what I hope you'll notice is to complete our answer, all we need to do is plug 3 into f prime. So using this as a function and writing it as f prime of something, this is 6 times something minus 2. We're plugging in 3 here. We're plugging in 3 here. This is going to give us 18 minus 2, which is equal to 16. And that tells us that our derivative in this situation is 1 over f prime of 3. That's going to be 1 over 16. So g prime of 21 in this problem is equal to 1 over 16. This type of example is a very common type of AP question. They do it in the way I've shown you here by giving you some information in a line or in the stem of the problem. The other very popular way they present this problem is they give you a table of data. And some of the data may be extraneous, you might not even need it, but you might see a table where, and let me just kind of draw this out. You might see a table where they give you x as one heading, f of x is another heading, f prime of x is another heading, g of x is the next, and g prime of x. And they might start giving you values for each of these and asking you to, and of course telling you that f and g are inverses. And then your job is to figure out which data points in this table do you need to help you fill in this expression right here. And by the way, that is the exact expression that you found in your textbooks when you're talking about the derivative of the inverse. Again, let me just kind of make sure that's really clear. We're going to copy and paste this guy. And let's bring this to this page, and we're going to paste this. There he is. Okay. Going back to the PowerPoint slide that I showed you earlier, it was the derivative of f inverse of x Well, that is a match to G prime. G is the inverse of F, so that's the derivative of F inverse. And then it's given as 1 over F prime of, so it's a perfect match. And the notation that's going to be in your textbook is the inverse function of F. Well, G is the inverse function of F. So I don't know about you, but I would much rather start with F of G of X equals X and take the derivative of that, F prime of something, copy the G of X, multiply by the derivative of the inside, G prime, and then make that equal to 1, and then manipulate this to get that guy. And I would much rather do that than try to memorize this expression here. Okay? So again, the whole purpose of this evening's session to me was to try to get you guys to have ways to get your students to not have to memorize these derivatives, but have a way to derive them and be able to come up with them. Implicit derivatives are the key to this. You can't do it unless you can get your students used to the notation. And the big part of that notation, again, is saying that the derivative of y is simply dy over dx. So I'm hoping that you guys...
Okay, I found this.
I'm hoping that you guys are very comfortable with this. If you have any questions at all, feel free to put them in the chat. Aside from that, we're going to wrap up for this evening, and I thank you for having some more calculus streams later on next week, and they'll be posted, so please come back. And if you have any topics at all that you want, that you're interested in seeing presented, either for your students or things that you want to see better ways or other ways of how you can present them to your students, put it in the chat. We'll be checking that all the time, and let us know what you want, okay? So thank you for joining us this evening. I hope you enjoyed it and got something out of it. If you have any feedback at all, if you enjoyed what happened tonight, please let us know in the chat, and we'll see you next time. Thanks so much.